In the first part of the Meson theory of exchange forces, we have discussed the fact that on the line of quantum field theory of electromagnetic and gravitational forces, Yukawa proposed that the nuclear force is arised due to exchange of pions between the nucleons. According to this hypothesis, for the nuclear force, virtual pions are the field particles, or in other words, nuclear force is mediated by the virtual pions. We have learned that inside the nucleus there is an exchange of pion between the nucleons. Three types of exchange we have discussed in first lecture. I am just repeating it. When there is a PP transformation, then neutral pion is emitted, and when a proton absorbs this neutral pion, you get again proton. Similarly, here we should write pi 0 this is actually the exchange of neutral pion. Again, N emits pi plus pion and converted into proton, and reverse is also true. Similarly, P emits the pi minus pion and converted, here will be actually pi minus to keep the charge balanced, and here should be pi plus, and this is neutron. These types of transformation takes place inside the nucleus. Already we have studied it, and these pions, that is pi 0, pi minus and pi plus, are the virtual pion. As I have told you, these cannot be detected there, and so these are called virtual pions, and these particles are actually the mediator of the exchange forces or nuclear forces inside between the nucleons. Now today we are going to develop a not simple, but you can say simplified Meson theory, which is known as One Pion Exchange Theory. One Pion Exchange Theory. One Pion Exchange Theory, OPE. One Pion Exchange Theory. Although more than one pion exchange actually takes place, but for the simplicity in the development of theory, we will assume only the exchange of only one pion, so it is known as one pion exchange theory. Actually, in this theory, we will discover a potential which is known as Yukawa potential, or it is also known as one pion exchange potential. Yukawa potential, we will discover it. Yukawa potential, and this is also known as OPEP, one pion exchange potential. Actually, the aim of this simplified theory is to find this very potential, which is also known as one pion exchange potential. Now how we will proceed? As you know, pion has a larger speed. We have assumed that its speed is equal to c in calculating the range of the nuclear force. So in fact you can say this the motion of this pion will be relativistic. So to find the wave equation, we need energy of the particle with which the wave is associated. And as the motion of the particle is relativistic, so we must use the relativistic idea or relativistic expression for the energy. So, and you know, in special relativity, we know the expression for the total energy of a particle if it is in relativistic motion. So, we can write the expression for total energy of the pion when we assume that its motion is relativistic. So, a relativistic expression. A relativistic expression for the total energy, TE for total energy, which is denoted by the symbol E of the pion is given as, you must have studied in special relativity, E square is equal to P square C square plus m naught pi square C square. This is actually the relativistic expression for total energy of any particle. Here I have taken the rest mass of the pion, so this is specifically for pion. And in this expression, what is this P? You know this P is momentum of pion. This is momentum of pion. Now, to find the wave equation, we must express this energy equation in terms of operator. As you know, in quantum mechanics, every observable is associated with an operator, or you may say a Hermitian operator. So we will here write the operator corresponding to the observables. So operators corresponding to with energy, the associated operator is what? It is in fact IH cross del T, and the operator associated with the momentum is minus IH cross del. These are the operators associated with the energy and the momentum. Now let us use these operators in equation 1. So using these in 1, or you can say the operator form of equation 1 will be what? You can see this will be E square. So this will be I square H cross S square del 2 by del T square, but I square is minus 1. So this will be minus H cross S square del 2 by del T square, and this equal to P square. So P square will be what? This will be I square H cross square del square, but I square will be equal to minus 1. So this is minus minus c square h cross square del square and plus m naught pi square c square. You know mass is not an observable in quantum mechanics, so this term remains same. Actually this equation 2 is nothing, this is simply the operator form of equation 1. Now we can set up a wave equation for this pion field. So to set up the wave equation, let us now introduce a scalar pion wave function, and that wave function let us denote by a symbol phi. So let phi of RT is a scalar wave function for the pion field. Actually, this scalar function phi of RT has the significance of potential and it is regarded as the field variable. And so, if we will operate this operator, let us see here, this operator on the wave function phi, then we will get the wave equation. So let us operate that operator on this function phi, which has actually the significance of potential. So what will be our result? This will be simply minus h cross square del 2 phi by del t square, and this is equal to minus c square h cross square del square phi plus m naught pi square c square phi. And you can rearrange the term in this equation taking the constant factor h cross square c square as common, and after rearranging you will get the result del square phi minus 1 over c square del 2 phi by del t square minus m naught pi square c square over h cross square phi equal to 0. Say this is equation 3. You can see actually this is a well-known equation which you have studied in relativistic quantum mechanics, and this very equation is known as Klein-Gordon equation. This equation which I have written in equation 3 is what? This is Klein-Gordon equation for a relativistic spinless particle. Spinless means spin equal to 0. we study it in fact relativistic quantum mechanics, and I hope you have done the course on relativistic quantum mechanics. And this is a very famous equation that is called Klein-Gordon equation. And as I have taken the expression for energy in case of relativistic motion, so actually this Klein-Gordon equation is for a relativistic a spinless particle, that is a particle whose spin is 0. Now you can see or you can check the validity of this equation. If we will take m naught pi equal to 0, actually pion is not a massless particle, but if we apply this very equation for a particle whose rest mass is 0, you can say if we want to apply this equation for the electromagnetic field, and the quantum of electromagnetic field is what? That is photon, and photon is massless. So in case of quantum of electromagnetic field, that is photon, you know, in that case m naught pi will be replaced by simply m naught, which actually represents the rest mass of photon, and we know it is equal to 0. So in that condition, this equation 3 will become what? We will take the last term in LHS of equation 3, 0, and our equation will become, which I am just writing here. So equation was 3 becomes, what this equation will become? This will be simply del square phi minus 1 over c square del 2 phi by del t square, and this equal to 0. You can see this is actually the well-known wave equation for the quanta of electromagnetic field, that is photon. And as in Maxwell's theory of electromagnetic wave, this actually represents the wave equation for quanta of electromagnetic wave, that is photon. And the simplest electromagnetic field is time independent, and this is called electrostatic field. In general, electromagnetic field is time dependent, but if we consider a particular situation or particular case when the field is time independent, you know, a time independent electromagnetic field is what? That is called electrostatic field. So in case of electrostatic field, actually electrostatic field is the simplest electromagnetic field. We know in case of electrostatic field, the potential function phi is not an explicit function of time. Phi not an explicit function of time. And if phi is not an explicit function of time, then what will be del phi by del t? You can say this will be 0. Here one thing must be arised in your mind, that why I have written del phi by del t but not d phi by dt. I have not written it, but I have written del phi by del t because we know this phi is although time independent, but this phi is space dependent. It depends on space. So phi may be a function of r, that is a space coordinate. So we must take the partial derivative, and so we say if phi is not an explicit function of time as in case of electrostatic field, in that very condition del phi by del t is 0. And this implies if del phi by del t is 0, then the second order derivative del 2 phi by del t square will be also 0. So in case of electrostatic field, this equation 4, which is in fact in general the field equation or the wave equation for the electromagnetic wave in case of electromagnetic field, but in particular case when we consider the simplest electromagnetic field, that is electrostatic field, then our equation 4 will become what? This will be simply del square phi equal to 0. So in this condition you can write in this condition that equation will become del square phi equal to 0. And this is a very important and very popular equation, very well known equation which you have definitely studied. This is known as Laplace equation. So this equation is known as Laplace equation. Laplace equation. And you know Laplace equation is applicable in that region or in that part of the space which is charge free. Laplace equation holds in charge free region. Charge free region. For example, if you take a capacitor, the space between the two plates of the capacitor is charge free, and you solve such problems by the solution of Laplace equation. So this very equation del square phi equal to 0, which is called Laplace equation, this holds in charge free region. But the problem which we are dealing here in present situation is not a charge free region. You know, inside the nucleus there is a charge distribution, and so definitely in this form of Laplace equation, using this form of Laplace equation, we can't handle this problem. So definitely we have to make some change. You know, if the region is not charge free, in that condition we solve the problem by using another famous equation which is known as actually the Poisson's equation. So here we will transform this equation in another form which is called Poisson's equations. But before transforming this equation in Poisson form, let us see what is the time independent part of the field equation which I have derived above. See this equation, equation number 3. In this equation, this is actually the time part of the equation, and so if we neglect this term which contains actually time derivative of phi, then we will get the equation which will actually only space dependent, because you know This del square operator is in fact a space operator. It represents the partial differentiation with respect to a space coordinate. So you can say that the time independent part, or in other words the space part of equation 3. What will be that? So let us see first of all the time independent part. The time independent part of, you have seen that was equation 3. Equation 3 is what? This will be del square phi minus m naught pi square c square over h cross square phi equal to 0. And we can write this equation in this form: del square minus k square phi equal to 0. Let us say this is equation 6a. 6a. Here the constant k square has been written at the place of m naught pi square c square over h cross square. So you can see that k is equal to m naught pi, this pi is in subscript, m naught pi into c over h cross, and we can write it as 1 over h cross over m naught pi c. And you have studied in the previous lecture that actually this quantity is denoted by R naught, and it is called range of the nuclear force. So this is simply 1 over R naught. 1 over R naught, where R naught is what? This is a range of nuclear force. A range of nuclear force. So this constant k is identified as the reciprocal of the range of the nuclear force. Now you can see the equation 6a, which I have just derived. This equation is valid in case of a Meson field in an analogous of Laplace equation, which is actually valid in case of electromagnetic field in the absence of charges. But as I have told you that in the present case, when we talk about the nucleus, so in that nuclear region there is a charge distribution, and as I have told you, this equation must be transformed into a Poisson's equation, in the form of Poisson's equation, which is valid in the region, or which is applicable in the region where charge is distributed. So the presence of charge requires the analogous Poisson's equation instead of the Laplace equation. And what is that Poisson equation? How we write it in CGS unit? Here I am writing it, the Poisson's equation. So the presence of charge requires not required but requires requires the analog of Poisson equation. Poisson equation. And what is this Poisson equation? This is actually del square phi is equal to 4 pi e rho. 4 pi e rho. Actually here E is the magnitude of the electronic charge. Magnitude means you have to take the positive value of electronic charge. Magnitude of charge of an electron. And what is this rho? Rho is actually the electron particle density. It means the number of electrons per unit volume. So this is electron particle density. You know, in a neutral atom, the number of protons is same as that of the number of electrons. So this represents actually the number of electron in unit volume, and this is charge of one electron. So this product E into rho will represent the charge in unit volume. That is called volume charge density. In SI unit, this equation is written as del square phi equal to rho over epsilon naught in general symbol. Here rho is already volumetric charge density, but here I have not used rho as volume charge density, but we have used it as the particle density, that is number of particles in unit volume. So this form is actually suitable here, so I am not writing the Poisson equation in this form. So this is actually the Poisson equation which we study in case of a time independent field in the region where charge is distributed. Now in our present case we have nucleon charges, not electronic charges but nucleon charges, and these nucleon charges are interacting with the pion field. So in this case we must use equation 6a, and equation 6a should be expressed as an analogy of Poisson equation. Not 6a is actually an analogy of Laplace equation for the charge free region, but if we want to transform that equation 6a, see the again this equation 6a. This equation 6a is actually what? This is the analogous equation of this Laplace equation for the Meson field. And as the nucleus is a region where charge is distributed, so we can't apply this equation. So we have to change this equation in the form of equation which is valid in the case of charge distribution. And you know the analogous equation for Laplace equation for charge distributed region is Poisson's equation. So definitely in RHS we will not have 0, but comparing with the Poisson equation we will write this equation 6a, which will be valid for the interaction of pion with the nucleon charges. So you can say in our present case we have nucleon charges interacting with interacting with the pion field. So we must write Poisson equation del square minus k square phi equal to 4 pi g into rho. Actually here there is a difference from the form of RHS of Poisson equation. In fact, in place of E, we have used the term G. What is this G? Actually, G is just an analogous quantity of E. It is a constant and it replaces the electronic charge in electrodynamics, and this G is known as effective nucleonic charge. Don't say nucleonic charge, but effective nucleonic charge. And it is also known as coupling constant. So G is identical to E, and it is effective nucleonic charge or coupling constant. This is also known as coupling constant. So we have transformed the Poisson's equation which we study in electrostatics in the case of the nucleonic potential. So this is the form which I have expressed in this equation, that is equation number 6b. Now for a static pion potential due to a single point nucleon at the origin, we can replace this product. You see here G into rho by a particular product of G and Dirac delta function. But this is a remarkable fact you have to understand when it is done. And I will first of all I am writing it here, and after that I will clear you why we do this. So you can say for a static pion potential, due to a single point nucleon, at the origin. Origin is arbitrary. Origin means r equal to 0. This G into rho is replaced by G into delta R. Where you know what is this delta R? Delta R is the Dirac delta function. Dirac delta function centered at r equal to 0. In fact, in general, we denote the Dirac delta function in 3 dimensions by delta r minus r naught. But here I have denoted it by delta r. It means r naught is 0. And when you use this symbol, you say that this delta function is centered at r equal to r naught. And here r naught is 0, so it is said that this delta function is centered at r equal to 0. And you know from the property of the Dirac delta function that this delta r is equal to 0 if r is not equal to 0, and this is in fact infinity if r is equal to 0. Or in other words, we also write its property as for a finite volume tau, the integral of delta r d tau is equal to 1. In fact, these are some of the important property or basic definition you can say of delta function. So you can see if r is equal to 0, then this delta function becomes undefined. And here, as I have assumed, first of all, let us see why this g into rho has been displaced by g into delta r. You know, if the charge distribution is continuous, in continuous charge distribution, then we define the volumetric charge density. Volume charge density can be defined in case of the continuous charge distribution. But if in any region there is a discrete distribution of charge and you want to find the charge density at a particular point, then how it can be defined? Actually, in that condition, you know, if we find a particular charge density at a particular point, the volume of the particular point is 0, so charge density should be undefined. And for this, if we want to define the volume charge density at this point, then we actually define it as the charge q. Let us say here is charge q into delta r. You know, if r is 0, this delta r will be what? This will be actually infinity, and q times infinity will be infinity. And this is the reason why I am replacing this factor g into rho by g into delta r. So in this case, particularly with the problem which we are dealing with, in this case the situation is just like that. We have considered that a particular nucleon is situated at a particular point, and so definitely g into rho factor must be replaced by g into delta r. In this condition, our equation which I have mentioned above, this equation is 6b, we should replace this g into rho by g into delta r, and that equation was equation 6b. So equation 6b becomes, what will be now this equation? This will be del square minus k square phi equal to 4 pi g into delta r. 4 pi g into delta r. Now we are in a seek to the solution of this equation 6c. One thing we must remember, that the force which I am dealing with, or the potential which I am dealing with, or any type of potential, definitely its effect becomes 0 when we take the test point at infinite separation from the source. So solution of that equation should be also written in such a way that the solution must vanish at infinity. In this condition, we write the solution of this equation for a point charge, or you can say point source. So for a point source of a strength G, say at R1. Point source of a strength G, say at R1. The solution of equation 6C is given as, this solution will be phi of R equal to minus G into e to the power minus k mod of R minus R1 over mod of R minus R1. Mod of R minus R1. Actually, see here, if we take this region as the field of the nuclear force, in this region nuclear force or nuclear potential is non-zero, and we take an arbitrary origin anywhere inside the field or outside the field, and this is our test point. Relative to this origin, its Poisson vector is R. Say this is test point P, and there is a source point here, as I have mentioned here. There is a point source of a strength G, and this is the point source G, and its Poisson vector is in fact R1. This vector is R1 with respect to. Then with respect to this point source, the position vector of this test point P will be what? This is actually R minus R1. And we are seeking a solution which should vanish at infinity. And so in that condition, when R will tend to infinity, this phi of R will be 0. And so I have written this in this form. Actually, if we not consider a point source, but we will write the general solution, so then what will be that for? General solution. General solution. But there is no need of general solution. We have a need of only this type of solution. But general solution of what equation? 6C. 6C is phi of R equal to minus integral over tau. This is in fact volume, let us say tau, e to the power minus k mod of R minus R1 over mod of, in general not write it here R1, but say R dashed in general. Here I have actually taken the source at the point R equal to R dashed. and this is r minus r dashed and g delta of r dashed and d tau dashed. Actually, in this case, there we have to take a volume element, and that volume element is d tau dashed. And due to that volume element, the potential at this point will be this much, and when we will integrate this potential due to this volume element at point P, we will get the entire potential at P. But this is general solution. But when we consider only a point source, not a charge distribution, in that condition we have written, if there is a point source, then this factor will be a constant, and as I have mentioned in the property of the delta function, that this delta r dashed and d tau dashed for the entire volume is equal to 1. So, if the volume becomes just a point charge, or you can say point source, in that condition the solution will be like defined in equation 7. So there is no need of this general solution here. I have only a need of equation 7. Now, in the light of this result obtained in equation 7, now we can find the potential energy of this system. Or you can say, if we assume the 2 point sources separated by a finite distance, then what will be the potential energy of that system? Now we can define, taking just the analogy of electrostatic condition. So now let us consider there are 2 point sources. Here is point source 1, and its Poisson vector is r1 with respect to the arbitrary origin, and here is but the point source we take, it is g, and here is another point source that is also g, and its Poisson vector is r2. In this condition, you can see, if we say that this is point source 1 and this is point source 2, in this condition the Poisson vector of point source 2 with respect to 1 will be what? That will be actually r1 minus r2. This vector is actually r1 minus r2. Now, the potential created by this point source, that is point source 1, at the site of the point source 2, if we assume that this is potential phi, if we will multiply this multiply this factor g by the potential phi, then we will get the potential energy. This is just an analogy of the electrostatic condition. Potential energy is equal to what? This is actually equal to charge q into potential v, q into v. Taking an analogy from this, we can find the potential energy or energy of interaction of these 2 point sources. So you can write, so potential energy of a source G at R equal to R2 in the field of the source G at R equal to R1 at R equal to R1 is given by this potential energy is V, and this V will be given by what? And in fact, quantum physicists tells this potential energy only as potential, but here I have used the term phi as potential, so I am telling it just potential energy. But this is actually, you will see this is actually Yukawa potential, which means potential energy. So this V will be what? Taking an analogy from this result, that potential energy is charge times potential, and here you know charge has been replaced by the parameter G, and potential at the site of second source due to the first source, and you know this potential is phi, and I am just writing phi of R2. It means this is potential at R2, and if this potential phi is due to this source, as I have assumed that is the source G at the place R equal to R1, then what will be the interaction energy? In that condition, you know that this separation will be changed. The separation between these two will be actually equal to R1 minus R2. So this V will be equal to, now put the value of this phi of R2, this is G, and this will be minus G e to the power minus K R1 minus R2 mod of R1 minus R2, and divided by mod of R1 minus R2, and sorry, here will be plus, this is G, and value of phi of R2 will be actually equal to this much. And so you can see this is a function of R, where R is what? This will be minus G square. I have just written the modulus of R1 minus R2 by R. So this is G square e to the power minus K R over R. And as I have seen previously that this K is actually the reciprocal of the range of nuclear force, which is denoted by R0. So you can write this expression as minus G square e to the power minus R over R0 and divided by R. This is our final result, and this very potential, which is defined in equation A, is actually known as Yukawa potential or the one pion exchange potential. So you can see the form of this potential, and now we will plot a graph between the potential function V of R and the parameter and the distance between the nucleons, that is R. So potential means potential energy defined in A is known as Yukawa potential or one pion exchange potential, OPEP. This is called one pion exchange potential. You can see if we will plot a graph of this potential with respect to R, graphical plot of V of R in against of R. you can see the functional form of this potential. This will be like this. When you know when R will tend to 0, see the expression, then actually V will tend to minus infinity, and when R will tend to infinity, then V will tend to 0. So the graphical plot is like this. Now if we compare this very potential, which is called Yukawa potential, to the well-known Coulombian potential. You know what is Coulombian potential? Coulombian potential. We know the Coulombian potential is given as some constant, or I am just writing the actual expression. The Coulombian potential has a form of Q square over 4 pi epsilon naught R. Remember, this is potential energy, so here is Q square. If this will be actually a potential in use the term in electrostatic, then there will be Q. So this is potential energy. And here we can see that this potential has also the property that when R tends to infinity, this V will tend to 0. When R will tend to 0, V will tend to infinity. Here I have used the positive sign, but this may be positive or negative both. But in this case, potential must be negative because the force is just attractive. But in this case, the force may be attractive or repulsive both. Although we know that nuclear force is also of repulsive nature, that depends on R, but the present result does not indicate that. So I am just mentioning here only the attractive nature. And the mathematical form, although the result at the infinity and at the limit 0 are same, but there is a difference in the form of the function. You can see that in the Yukawa potential there is an exponential function present, and that exponential function actually decreases with increase in R. As you have seen that Yukawa potential has the form of minus g square e to the power minus kr over r, or you can write r over r naught. So this potential, if this term were not present, then the form of the potential Yukawa potential will be exactly same as that of the Coulombian potential. But due to the presence of this exponential factor, the potential defined by the Yukawa potential, you can say, and the Coulombian potential differ much. Actually, with distance, the Yukawa potential varies more rapidly due to the presence of the exponential factor. So this nuclear potential, you can say, decreases more rapidly with distance from the source than the Coulomb potential. And the reason is what? The reason is the presence of the exponential factor. But in when R is very small, then there will be no difference between the Coulombian potential and the Yukawa potential. So when you can say that as the separation is very small in comparison to R naught, then these two potential vary in same manner. So for R less than R naught, both potential vary in similar manner. Similar manner. So we have found the expression for Yukawa potential, and actually this, when you will take the space derivative of this potential, you will get the expression for nuclear force. But in quantum mechanics, we always talk about the force in terms of potential, not in terms of actual force. Potential, when you define potential, it means you are defining the force. So, and now after this simplified theory, we will see some important remarks regarding the nuclear force which have been found from the Yukawa's Meson field theory. So you can say the important remarks regarding the nuclear force. Important remarks regarding the nuclear force. The first remarkable fact is that there are three types of interaction according to this theory inside the nucleus, which is responsible for the nuclear force, and those three types of interactions are NN interaction, NP interaction, and PP interaction. Actually, all these three, in case of all these three interactions, the nuclear force is same, or you can say equal in magnitude. And the reason behind is that the nuclear particle does not change its charge during this interaction. So nuclear force is same in all these three interactions, as the nuclear particle does not change its charge. And from this we also gather another important information, that the nuclear force is charge independent. Nuclear force is charge independent, because when we talk about the NN interaction, both particles are chargeless. When we talk NP interaction, one is charged particle, that is P, and another is uncharged. And when we take the interaction PP, then both particles are charged. But as we have seen that the force, nuclear force, is same in all these three interactions, which actually implies that the nuclear force is charge independent. Again, as we have seen in the very beginning of this theory, that we can calculate the range of the force from this theory if the mass of the meson is known, and the value of range is 1.4 f. So actually this theory gives an information about the range of nuclear force, and it according to this theory, nuclear force is short range. So the another information we gather from it is nuclear force is short range. and you know this R naught is actually equal to 1.4 F. The next information which we get from this theory is the large coupling constant, as I have mentioned previously, that the coupling constant in case of a strong interaction is given as G square over H cross C, and its value is almost 17. Actually, this larger value of coupling constant suggests that more than one meson is transferred simultaneously between two nucleons. But in this theory, as I have told you earlier, that more than one pion can be transferred, but we have considered the transference of the only one pion, and so the potential obtained is known as one pion exchange potential. But the real situation is not this. Actually, the larger value of coupling constant suggests us that more than one meson is transferred simultaneously between the two nucleons. So, you know this G square by H cross C, which is actually 17, this is coupling constant, and this value is very large. This implies more than one pion is transferred simultaneously between two nucleons. One of the most important information we gather from this theory is that the nuclear force has a actually repulsive core. Nuclear force has a repulsive core, or you can say for very small separation between two nucleons, that is a separation much smaller than the range of the nuclear force becomes repulsive. How we can predict it from this theory? Actually, you have seen that the one pion exchange potential is defined in terms of the delta function, and due to this delta function, this repulsive core arises. So you can say for small distances, a repulsive core arises from delta function. So these are some important remarks regarding the nuclear force which we gather from this Meson exchange theory. Now this theory has actually some shortcomings, or you may say drawback. Actually, in the very beginning, I have told you that I am just discussing a very simplified theory of simplified exchange theory proposed by Yukawa. In developing this theory, we have taken so many assumptions, and so the larger number of properties of nuclear force cannot be interpreted by this simplified theory. It does not mean that Yukawa's theory cannot explain the other properties, but for this we have to take the rigorous form of this theory, which I have not just mentioned here, but so many theoretical physicists have developed this theory by taking the several factors taken into account. So the theory in its simple form cannot explain something, some important property of the nuclear force. In the simple form, the first shortcoming is a spin dependence of nuclear force. A spin dependence of nuclear force. As I have told you, it does not mean that this theory cannot not explain the spin dependence, but the theory which I have discussed in simple form, that is unable to explain the spin dependence of nuclear force. But when this theory will be rigorously explained, then spin dependence can be explained. And the another important property of nuclear force is its non-central character or non-central nature. But this simplified theory is unable to explain the non-central nature, or you may say the tensor force nature of the nuclear force. So non-central nature of nuclear force. This theory, this simplified theory is unable to explain the non-central character of the nuclear force. As I have told you, to account these properties, if we have to account these properties too, our aim is to explain these properties from this very theory, then this theory should be modified. Actually, several theoretical physicists have modified it, taking the so many parameters to develop this theory. Some of that parameters are, if the theory is modified, number one, the tensorial character of the Meson field wave function. If the tensorial character of the Meson field wave function, this is taken into account. Actually, then you can see this non-central character of nuclear force can be explained. And at the same time, some theoretical physicist has taken into account the isobaric spin character. Isobaric spin character of the Meson field wave function. And if this is taken into account, then the spin dependence of the nuclear force can be explained. But in this lecture, I have not taken these into account. But when we will study in some detail, then we will take these parameters too, and after that we will be able to explain these properties of nuclear force. So this is all about the simplified theory of Yukawa regarding the nuclear force, which is actually called the Meson exchange theory of nuclear force. And in next lecture, we will discuss the non-central nature of the nuclear force, or you may say tensor force.